The world's premier semiconductor equipment supplier has now combined technology, nature, and more than 25 years of experience in radiant heating technology to advance RTP into the next century. Introducing the RTP Centura with the honeycomb source from Applied Materials. Wafer fabrication is advancing at a rapid pace in today's semiconductor industry, requiring several hundred processing steps before completion. Many of these steps are thermal processes. As device geometries continue to shrink, the thermal exposure must be reduced. Rapid thermal processing, or RTP, was developed to minimize a wafer's exposure to excess thermal energy. This is achieved by using thermal ramp rates up to 1,000 times faster than a standard batch furnace. The challenge for RTP is how to ramp quickly while maintaining temperature uniformity. Present-day RTP systems use a single non-contact optical pyrometer to measure a wafer's temperature at the center. This single-point measurement, however, can't sense center-to-edge temperature differences. The result is non-uniform heating, which causes slip defects and undesirable process variations. A second problem with conventional optical pyrometers is that they fail to adjust for the variation in the backside emissivity of the wafer. Maintaining temperature control from wafer to wafer requires backside etching of the films, or a measurement of the emissivity and an adjustment to the production process. Applied Materials has introduced a new rapid thermal technology, the RTP Centura with the patented honeycomb source, offering significant improvements in three main areas. The first is in wafer heating control, using our patented honeycomb source. This RTP Centura lamp module replicates the structural strength and space efficiency found in a beehive honeycomb. The light source contains 187 variable intensity tungsten halogen lamps, each housed inside a collimating light pipe. This provides the high spatial resolution of the light intensity pattern required for thermal uniformity in combination with the high optical power density required for fast thermal ramps. The second area of improvement with the RTP Centura is that temperature is measured by multiple non-contact optical probes positioned beneath the wafer. A multi-input software controller readjusts the individual lamp zones at a rate of 20 times per second to maintain thermal uniformity. This plot of lamp voltage versus lamp group shows that the center-to-edge power distribution required to achieve uniform wafer temperature varies dramatically for different parts of the thermal cycle. The RTP chamber has a programmable variable temperature ramping capability of up to 75 degrees C per second, with a ramp uniformity of better than plus or minus 2 degrees C. Steady state temperature uniformity is typically better than plus or minus 0.5 degrees C. The result is the most uniform thermal wafer processing possible in the industry today, and a process that's guaranteed to be free of lattice slip defects. The third area of improvement is in the RTP Centura's ability to adjust for the changes in emissivity of the backside of the wafer. We've solved this problem by designing the RTP Centura chamber to measure temperature independent of wafer emissivity, thereby greatly improving wafer-to-wafer repeatability. This simplifies the production process, eliminating the need for backside etches and emissivity checks. The Applied Materials RTP process module is designed for integration on the Centura mainframe. The RTP Centura system utilizes dual independent vacuum load locks that can each hold up to 25 wafers. Located in a sealed high-purity transfer chamber, a magnetically coupled dual-speed robot provides precise movement of wafers, maximizing throughput and minimizing contamination. The high-purity environment eliminates the need for lengthy chamber purges. Wafers enter the process chamber and are then lifted by 3 quartz pins. The robot blade is withdrawn and the pins lower the wafer onto the edge ring. Rotation of the ring and wafer during processing results in excellent process uniformity. The robot end effector is made of high-purity quartz, allowing removal of the wafer at temperatures as high as 800 degrees C. The wafer is then moved to a cool-down station prior to placement in the cassette. The 3 major applications for the RTP Centura system are ion implant anneal, silicide anneal, and oxidation. Results on source drain implant anneal show more precise control of L-effective dimensions, a requirement for submicron devices. Multi-point temperature measurement ensures wafer-to-wafer repeatability of less than 1 degree C. Annealing of titanium silicide films improves with the RTP Centura in process uniformity and repeatability. Added non-uniformity is controlled to less than 1%, independent of wafer backside films. Creation of thin film oxides for use as the gate oxide was not previously achievable with RTP technology. However, with the Applied Materials RTP chamber, oxide uniformities of better than 1% are achievable. High throughput, excellent uptime, and very low maintenance make the RTP Centura a high productivity, low cost of ownership tool. Marathon customer tests have shown the system capable of running over 130,000 wafers without preventive maintenance. There is only one RTP system that provides backside emissivity independent temperature measurement, multiple sensor control loops for complete wafer temperature control, on a high-throughput, reliable wafer handling platform, with benefits that include superior process performance and yield, and reduced cost of ownership. The RTP Centura with the honeycomb source, only from Applied Materials, advancing RTP technology into the next century.